In this game, you have a grid expanding in all directions infinitely. In the middle, there is a red horizontal line, and under the line, infinite pegs. And these pegs represent the soldiers of the game of Conway Soldiers. Every square of the grid can contain only one peg at a time, and you start with the entire space under the red line completely filled with pegs. Your objective is to move the pegs over the red line and go as far as you can. For example, if you reach the first row over the red line, you reach level 1. If you reach the second row, that's level 2, and so on. This is how movement works. In order to move, a peg has to jump over another peg. After the movement is done, the peg that got jumped over is removed. You cannot jump diagonally and you cannot jump over more than one peg. So basically, there are just 4 possible moves, these ones. I will also link in the description a page where you can try the game for yourself and see how far you can get. Well, how far do you think you could actually get? Level 1 is easy, you just make a single move up. To reach level 2, you use another peg to jump over the other peg that reached level 1. Now I'll show you how to reach the next 2 levels. Keep in mind that there are multiple ways of reaching rows 3 and 4. The ones I'm showing here are the most optimal ones, so using as few moves as possible. If you're wondering, here is a table with the minimum number of moves you need to reach each level. But what about level 5? If you try for a bit, you will notice that it's pretty difficult to do it. You can get close to it, but you never quite reach it. Instead of trying ad nauseum, it would probably be more efficient to just find a way to prove whether it's even possible to do it or not. Which is what I'm gonna do for half of this video. If at any point of the video there is something you don't understand, write me a comment and I'll try to answer. In order to prove this, you need to understand what an invariant is. First of all, I'll give a definition. An invariant is a property of one or more objects that doesn't change when operations or transformations are applied to those objects. Also keep in mind that an invariant is a number. So let's make a very stupid example to make you understand this. Let's say you have a 2x2 board and just one peg on it. I'm not talking about Conway Soldiers now, I'm just making up another game to explain the concept of invariance. In this new game, you can move your peg in whatever direction you want, even diagonally. It can move only by one square at a time, and it cannot exit the board. And that's it, those are the rules. You need to find a number that doesn't change even when the peg moves. So here's what you can do. Write the number 1 on every cell of the grid, and now you could say that your invariant is the number of the cell where the peg is currently on. For example, right now that number is 1 because the peg is on a cell with 1 written on it. But even if the peg moves, the number is going to remain 1 because on every cell of the grid you have the number 1. So this number is an invariant. You know that, no matter how you move, it cannot change. And what if you had multiple pegs? Well, the invariant would still work. Let's say you had 2 pegs. Now, what are the numbers of the cell with a peg on it? The first peg is on a 1, the second peg is on a 1, so you get 1 plus 1 equals 2, and that's your invariant, and it's going to remain the same. So now imagine doing this with Conway Soldiers, writing numbers on the whole infinite board and finding an invariant by summing all of the numbers of the cells with pegs on them. Clearly this is much more difficult, not only because the board is infinite, but also because every time you move, a peg gets removed. Now, maybe you're wondering, what do we even need an invariant for? So let's return to my stupid example with an invariant of 1. This time, I will also add a victory condition. You win the game if you can occupy these 2 cells at the same time. Can you do it? Well, you can actually prove that winning is mathematically impossible, because what would happen if you actually won? You would have 2 pegs set up in this way, and thus your invariant would now be equal to 1 plus 1 equals 2. But right now your invariant is 1 and you know that it can never change, so it's impossible to win. So here's the objective with the proof of Conway Soldiers. First you find an invariant and also write the right numbers on the grid so that the invariant works. After this, let's say that all the cells of row 5 have the number 1 written on them. It's an example. That would mean that even if you reached level 5 with just one peg, your invariant would have to be at least 1, but ideally more than 1. If the invariant were more than 1, then that would be fine. For example, if the invariant were 2, you could have a peg on row 5, which would give you a value of 1, and then you could have some other pegs scattered around the board, which summed up could give you the value of 1, and so you could have 1 plus 1 equals 2. But if the invariant was less than 1, then you would straight up know that reaching level 5 is impossible. Obviously, to find this invariant, you will have to sum all of the numbers of the cell with pegs on them, which in this case are infinite, so that's another complication. But now that you know what an invariant is, I can finally get to... In the previous example, I said to imagine all of the cells of row 5 having the number 1 on them. But actually, it's not necessary to take the entirety of row 5 as the goal. Since to win level 5 you just need to reach row 5 with even one peg, I'll just take one random square of row 5 and mark it as the goal. From now on, this is the square you're looking to reach, no more row 5. I chose this square randomly because, since this grid is infinite, they're all the same, there's no center square or anything, so whatever square you choose is not going to impact the proof. The first thing to do is to find which numbers you will have to write on the grid in order to make the invariant work. Writing completely different numbers clearly isn't going to get you anywhere. This is because you need to know which numbers are written on the whole infinite board. Let's say these numbers that you're seeing on screen were the ones you wrote. In this case, there would be a problem. What if, now, I ask something like... Can you tell me what number is written in the 200th cell in that direction of that row? You wouldn't know the answer unless you went in and checked. One useful thing to do would be to write x on the goal, then write x plus 1 on the near cells, then x plus 2 and so on. Now you know which numbers are written on the distant cells. You still don't know how much x is, but you can find out with an equation. Every time you move in this game, 2 cells get emptied and 1 gets filled. On the turn before, you had these 2 cells occupied, and now you have just this one. So in order to maintain the invariant, the sum of the values of these 2 cells would have to be equal to the value of the other cell. For example, if the 2 red cells had both a value of 1 and the green cell had a value of 2, so the sum of the red ones, you would have an invariant of 2 which doesn't change. Let's take this reasoning to the grid. X is the cell you have to reach, the 5th row cell. You have 2 pegs in x plus 1 and x plus 2. You make a jump and land on x. So to make this work, x plus 1 plus x plus 2 must be equal to x. Now this is a simple equation that can be solved. Here are the steps. X equals minus 3. So now you have your number. If you try it out, you will see that in this case the invariant doesn't change. But does it work every time? Here's another example. 2 pegs in minus 1 and 0. You jump and reach minus 2. And clearly this time the invariant has changed. So there must be something wrong here. As it turns out, the right method to do this is to use exponents. If you don't know what they are, I left you a video in the description explaining all you need to know, properties and stuff. On the first cell, you put x to the power of 0, which is 1. In the adjacent cells, you put x to the power of 1, then x squared, and so on. Why is this better? Returning to the previous example, this was the first case with its equation, and this was the second case and its equation. If you solve them, you will see that they result in different numbers, and that's because they are not equal. Now take the 2 cases of this example to the other board, where exponentials are used. You now have these 2 equations. If you solve them, you will see that this time they're actually equal. Here's the proof. Take the second equation and divide by x on both sides, and there you go. And what if you take the equation of another move, like x to the power of 5 plus x to the power of 4 equals x cubed? Well, you can still get to the first equation if you divide everything by x cubed. In fact, you can always get to the first equation. So this means that if you can find the answer to this equation, then you automatically have the answer to all of the other possible equations. Except for stuff that goes in the other direction. If you jump from x to the power of 1 to x cubed, you already have a different equation. But why would you ever want to do that? If you take a look at the methods to reach the first 4 levels, you will observe that you never need to make a move that is not towards the goal. So I'll ignore those moves for now, but I'll talk about them again at the end of the proof. Back to the equation. Bring the 1 on the other side, and now I've got a pretty basic setup that I can solve using a thing called quadratic formula. It is a widely known formula and usually it is studied in high school or even sooner, so I'm not going to explain it here, but I will leave a video in the description so you can take a look at how it works. All you need to know for now is that using this formula I can find out 2 possible results of these equations, and one of them is -1 plus square root of 5 divided by 2, which is a very particular number that could ring a bell if you know a bit about math. That's because there's a number called the golden ratio, which pops out in a lot of mathematical problems and also in nature and other subjects as well, and this number is equal to roughly 1.6, but you can also express it as 1 plus square root of 5 divided by 2. Very similar to this other number. Is there some correlation between the two? As it turns out, there is. Take the value of the golden ratio and put it as the denominator in a fraction with numerator 1. This type of fraction is called the reciprocal of the golden ratio. So you have this number, which is like saying that you have 1 divided by the golden ratio. With fractions, a division becomes a multiplication when you swap the 2 numbers on the second fraction. And so you get 2 divided by 1 plus square root of 5. Multiply it with 1 minus square root of 5 divided by 1 minus square root of 5. This fraction is equal to 1, so if you multiply it by the other fraction, you're not changing its value, you can do it, and this is called rationalization. On the numerator, nothing can be done, but it's possible to solve the multiplication of the denominators. 1 times 1 is 1, then 1 times minus square root of 5, 1 times square root of 5, and square root of 5 times minus square root of 5, where the square root cancels out and you get minus 5. These 2 numbers cancel themselves out because they're opposite, and you're left with 1 minus 5, which is equal to 4. Now simplify the 2 and the 4, and you get this number. And if you change all of the signs of the number, which is another thing you can do while still maintaining the same value, you get one of the 2 results of the quadratic formula I solved before. So I just proved that the result of this equation is the reciprocal of the golden ratio. Finally, you can start filling up the whole grid. Now, maybe you're wondering why the golden ratio is so cool and useful. There are many reasons, but one of them is important for this proof. And that's the fact that if you take the golden ratio and add 1 to it, you get the golden ratio squared as the result. Now, this also means that the golden ratio is equal to the golden ratio squared minus 1, and it also means that the golden ratio squared minus the golden ratio is equal to 1. Keep these 3 equations in mind. You've just got 2 lines now, but at least on those the invariant is not going to change if you move towards the goal. But what about the rest of the grid? Clearly it has to be filled with other variations of reciprocal of the golden ratio to the power of something. To make this shorter, from now on I'll refer to the reciprocal of the golden ratio as just x. So what can you do here? Well, take this x here, write x squared to both its sides, then x cubed, and so on. Then do this same process for the other numbers in line. And now, same process for the other side of the board. Both horizontal and vertical movements are now fine, if going towards the goal. If you notice, the exponents on the axis of every square are equal to the number of steps you would need to take to get from that square to the goal using the shortest possible path. Keep that in mind. And finally, the board is filled. But before I go on with the next topic, there's still an extra thing I want to talk about. Take the square of the board. What is the number in it? X to the power of what? The only way you have to know is to go in and check. But the mathematical way these numbers have been calculated is using Manhattan geometry. Take a look at the grid. You could say that in some way it resembles a Cartesian plane. Sure, the dots aren't on the lines, they're on the spaces, but still, you could say that, for example, this point has coordinates 2 and 1. If you don't know how Cartesian planes work, I'll leave you another video in the description. So, in this case, these two lines of the grid will be the Cartesian plane's horizontal and vertical axes. I just determined them randomly. From there, you can get the coordinates of all the other points. The goal's coordinates, for example, are 0 and 5. Let's say you want to know the exponent of the square with coordinates 3 and 3. Here's how you do it. First, you subtract the coordinates respectively, so the x of one point gets subtracted from the x of the other point, and then you do the same with the y's. It doesn't actually matter which of the two numbers gets subtracted from the other, because then you take the absolute value of the two numbers. Taking the absolute value means that if the number is negative, it becomes positive, and if the number is positive, it remains positive. So 5 minus 3 and 3 minus 5 give you the same result if you take their absolute values. That's why the order with which you do this subtraction is indifferent. So then, you take these two numbers and add them together. And there you go, you have your exponent. And this works every time. But why? Remember when I said that every exponent is equal to the shortest path to reach the goal? Well, Manhattan geometry is the way to calculate that distance. Think about it. First you're calculating the difference between the x's and the y's of the two coordinates. So basically you're finding out what the height and width difference of the 2 points is. 2 points on the same space will have 0 difference both in height and width. From there, if you just go up, you'll gain height difference. You will gain it even if you go down, and that's why you take the absolute value of the two numbers. Then if you go right, you will gain width difference, and then if you sum the two numbers, you will get the total difference. And that is the 2 points Manhattan distance. Now it's time to tackle the invariant problem. As previously stated, if you move towards the goal, the invariant works, but if not, it changes. There are two types of moves that change the invariant. The first is moving in the other direction of the goal. Let's say you have two pegs at x and x squared. If you jump to the goal, everything is fine, because x to the power 1 plus x to the power 2 equals 1. But what if you jump to x cubed? Now you're substituting x to the power 1 plus x to the power 2 with a smaller number, which is x cubed. That means that the invariant has decreased. The other type of moves you could do would be to, for example, jump from x to the power 2 to x to the power 2. After this move, you haven't moved towards nor against the goal, because the square where the peg was has an equal distance from the goal to the square where the peg is right now. And yet again, the invariant has decreased. So, if you move towards the goal, the invariant doesn't change. If you move away from it, it decreases. If you move but the distance doesn't change, it decreases. These are the only three possible types of moves, so that means that the invariant can never increase. That also means that the invariant is not a real invariant, it's actually another thing called a decreasing monovariant. But luckily, that works just as well. You know that the value of the goal is 1. So if you discover that the dm decreasing monovariant is equal to a number which is smaller than 1, then you know for certain that the game still cannot be won. That's because the only way to reach 1, thus changing the value of the dm to at least 1, would be to make it increase, which is not possible. So the dm is less limiting than the invariant, but it could still work. And now it's finally time to calculate the value of the dm. To do that, you need to sum the values of all the squares occupied by a peg, which are infinite. Here's how to do it. First, calculate the sum of all the values of this row, starting from the 1 and horizontally going on forever. The equation for it is 1 plus x squared plus x cubed plus etc., where the dots represent the fact that the addition goes on forever, equals s. And obviously the objective is to find the number s. So multiply both sides by x. Now, do you know how polynomials multiplications work? Basically, if you're multiplying a number and a polynomial, you take the single number and multiply it singularly by every member of the polynomial. So the result of this operation is x times 1, so x, plus x times x, so x squared, and so on. Notice that this new addition is equal to the previous addition but without the 1. And this new addition is also equal to xs. So you could say that if you take this addition, which is xs, and you add the number 1, you get this other addition, which is s. In other words, s equals xs plus 1. Let's make xs change side. Take s minus xs, divide by s and multiply by s so that the result remains the same, you get s multiplied by 1 minus x. Now divide by 1 minus x on both sides and you have your result. Now, as established before, x is equal to 1 divided by the golden ratio. So in this case, you get 1 divided by 1 minus 1 divided by the golden ratio, or GR for short. Now, if you remember, when I solved this equation, I found that its result was 1 divided by GR. So you can substitute that number to the x's and have this new equation. This is going to change sides. And now you know the result of this other addition. 1 minus 1 divided by GR is equal to 1 divided by GR squared. And 1 divided by that is equal to GR squared. So that's the value of this half line. What about the other half line? Well, notice that the two half lines are equal except for the fact that one is being added to one and the other is not. So this half line is equal to the value of the other half line, which is GR squared minus 1. Remember the three equations from way before that I said were going to be useful? Take a look at them now. GR is equal to GR squared minus 1. Those are the values of the two half lines. To find the value of the full line, simply add them together. So GR plus GR squared. Divide and multiply by GR, you get GR multiplied by 1 plus GR. And again, looking at the three equations, the result is clear. 1 plus GR is equal to GR squared. And now you have GR multiplied by GR squared, which is equal to GR cubed. So that's like saying that 1 plus x plus x plus x squared plus x squared plus x cubed plus x cubed plus etc. equals GR cubed. What if you multiply both sides by x? On the left side, you get all the numbers from the line below. You know that for certain because, as you go down the grid, the exponents of the x's are increasing by 1 every line. So every new line is like the line before, but multiplied by x. That means that the value of this line is xgr cubed. X is equal to 1 divided by GR, so you get this multiplication, which becomes GR cubed divided by GR, which is equal to GR squared. That's the value of this line, and by value obviously I mean the value of all the numbers of the line added up together. Now same thing, value of the next line is going to be GR squared times 1 divided by GR, which is GR. Next line is 1, next line is 1 divided by GR, and the first line under the red line is 1 divided by GR squared. Now you can forget the values of the previous lines, they were only needed to get here, where the pegs are. First line of pegs is 1 divided by GR squared, second is 1 divided by GR cubed, and so on forever. Now add up all these lines and the result is going to be the dm. This is the addition. Now remember that x is equal to 1 divided by gr, so I'm going to rewrite this addition to make it simpler. Now divide and multiply by x. And now if you notice, this addition is equal to the one saw before. It's s in fact, and we already found out that s is equal to gr squared. 1 divided by gr squared times gr squared is equal to 1, so the dm is 1. To summarize, the sum of the values of all the squares with pegs on them is 1. During the course of the game, no matter how you move, this number is not going to increase. It could decrease or stay the same, but the goal has the number 1 on it. So if the dm can never increase, that means that if you have one peg on the goal, that's the only peg you have on the whole board. To reach the goal, an infinite amount of soldiers get jumped over, thus disappearing, which means an infinite number of jumps has been made. And that's the proof that you cannot reach row 5 in a finite number of moves, which is what John Conway, the creator of the game, wanted to prove. But what if you have infinite moves and infinite time? First of all, this problem must be formalized. That means expressing this problem not using words, but mathematical symbols. This is important because words sometimes can be ambiguous and misunderstandable. The objective is to formalize not only the game, but also its rules. This way, whenever something weird happens, you can just check the formalized rules and see if it's allowed or not. And now that we'll start playing with infinity and infinite quantity of pegs, it's important to have a clear and non-confusing set of rules. Here is a brief introduction to this mathematical language. To name a point on a graph, you use x, y. This is a single point. The x and the y are fixed values. If I tell you that x is equal to 3 and y is equal to 2, then you know that this point has coordinates 3 and 2, and where it is on the plane. But now I will enclose this point into curly brackets, and now its meaning is completely different. The curly brackets represent a set. In this case, the set of all possible points on the graph. This time x and y aren't fixed, they can have any value. For example, x equal to 3 and y equal to 2. This is one of the points in this set. X equal to 183 and y equals 11, that's another, and so on for eternity. If I told you to put a peg on every point that is included in this set, you would just have to cover the whole grid. By the way, as you probably have noticed, now I'm putting the pegs on the intersections between the lines and not on the squares anymore. This is to make it easier to understand, since this chapter is going to have a lot of coordinates and graph-related situations. But the situation is the same. These are the x and y axes, this is the red line on y equals 0, and this is the goal with coordinates 0, 5. Here's how to get your initial starting point. Put a peg on every point included in this set. What does this mean? Here you're still taking every possible point in the whole board, but this time there's a condition. The 2 points means if. So, you can only take this point into the set if its y is less or equal to 0. Let's make a couple of examples. Is this point into the set? Yes. Is this point into the set? No. And so on, again for eternity. At the end, these are the pegs you get, so that's correct. If you remember, the red line is on y equals 0, so all points there and under have a y value equal or less than 0. Now, since I talked before about formalizing the rules, here is the list of the rules of the game. Number 1. Change of state occur by moving. A point can have 2 states in this game. It can have a peg on it or it cannot. So, a change of state is when you're passing between those 2 states, so changing from one to the other. Obviously, a change of state can only happen when you move a peg. 2. One move at a time. To limit the game a bit, it is better if you cannot move various pieces at the same time, otherwise stuff like this could happen. 3. Each point is involved in a bounded number of moves. This means two things. First, that no point can change status an infinite number of times during the game. Second, that there exists a certain number n, which is the same for all points, and no point can change status more than n times. Now, this rule is very specific. Want to know why? Well, it would probably take another video, so write me a comment if you would like to see it. But basically, if the rule wasn't there, you could create a peg out of thin air. 4. There are only 4 types of moves in this game, these ones. 5. There is a starting position. This has already been formalized, I showed it before. 6. There is a winning position, which is going to be reaching the goal. These are the rules that have to be formalized. To make it easier, it is essential to define a function. So, here's a brief explanation of what's a function. Here's an expression, x plus 1. In this case, x is a variable and it has infinite values. It could be any number. So, here's the function of this expression. And if I plug the number 2 into the function, the result is going to be the expression associated with the function with the number 2 instead of the x. And so the result of f2 is 3, and so on. Generally, you can say that this is the x function because it changes the variable x of this expression. Had the expression had multiple variables, you could have had a function x and a function y, or a function xy. Now I'll make 3 moves, and I have to remember to not make them all at the same time, so at 3 different seconds I will make these moves. And now I will define a function which is just perfect for my situation, for my game. Here is the function xyt. No matter what numbers you plug into this function, it can only give you either 1, 1/2 or 0 as a result. This function is useful because it tells me precisely the state of the board at a certain time. For example, now I'm at the 3rd second, right? I just made this move. Take this point, the coordinates of this point are 2 and 2, so I will plug in the x and y of the function, the x and y of the point, so 2 and 2. Then on the t value of the function I will put 3, which is the 3rd second of my game. As a result, the function will give me 0, and 0 means that that point is empty. The function is correct because at the 3rd second of my game, the point with coordinates 2 and 2 was empty. Another example, let's return to the 1st second and plug this point in the function, coordinates and time. The function will return 1 this time. But if I plug the same coordinates in a different time, the result could be different. If I plug in the coordinates of a point which is changing state in that exact second, the result will be 1/2. Now, you may be thinking that this function is simply amazing, that it's an incredible coincidence that it perfectly defines the board of the game you played at any precise instant. Can I see the expression associated with it? Well, no actually. That's because nobody knows what the expression is. In fact, it's not important to know. I just need to say that out there somewhere there exists a function that perfectly defines my game. And this function will be useful for the formalization of the rules. And in fact, I'll do that now. If the function xyt is equal to 0 and the function xyu is equal to 1, then there has to be a function xyv which is going to be equal to 1/2. In this case, x and y are fixed values, so imagine that the same 2 coordinates have been plugged in all 3 of these functions. So we're talking about the same point, but in 3 different moments. There's a first moment, the moment t, where the result is 0, so there's not a peg on it. Then in another moment u, which time-wise comes after t, since u is bigger than t, the same point has a peg on it. So there has been a change of status. That means that there must have been a moment v in between the moments t and u where that point was changing. So basically you're saying that if there is a point that was 1 or 0 before and now its status is changed, then there must have been a move that changed it. I know it sounds pretty obvious, but again, it's formalizing. In simpler terms, you're saying that you cannot do something like this. At any point, this set has either 0 or 3 elements in it. So remember, this means take every point on the board and put it in this set if the coordinates of that point plugged into the function with the current time give you 1/2. Basically you're saying, put this point in the set if the function says that it's changing right now. And how many elements can this set have? Well, either you didn't move in that moment, so 0, there have been 0 changes of status, or you made one single move, so 3. Think about it, every move you make changes the status of 3 points. The peg that's jumping, the peg that's being jumped over, and the point where the peg is landing. If you could make 2 moves at the same time, then the number could be 6. But here, it says that it can be either 0 or 3, so 1 move at a time. For every point, this set is equal to n. So basically you're saying, take the t, so the time, if when plugged into the function, it gives you as a result 1/2. So take the time if the point on that time was changing. So this is the set of all the times when the point was changing. And as said before, this set cannot be infinite. In fact, it cannot even be bigger than this number n. And this is true for all points. Every time 3 points change status, which means a move has been made, the 3 points can either be these ones or these ones. Taking the first case as an example, there is a certain point, then another point which is at the same height but just behind, and another point which is just ahead. In this way, the rule is already covering 2 of the 4 possible moves, this one and this one. The other set covers the other 2 moves. It's also necessary to say that when a move is being made, the central point must always change status from 1 to 0. This prevents a player from doing something like this. This one has already been formalized. And this is simply f05t equals 1, a moment t where the goal has a peg on it. Before I go on with the proof, there is a logical conclusion that must be made. This is not part of the rules, but it's a thing that I want to stress, since it will be important in no time. Imagine this particular configuration of pegs. This peg can be jumped, so you make a move and end up in this other situation. Right now, you're going forward in time. You're simply playing the game normally. Here's another configuration. One single peg. You cannot do any moves with only one peg, but you can imagine which other configuration of pegs led to this particular configuration. For example, this is a possible one. This configuration leads to this other one. Here's another example, and here's another one. But if you notice, this configuration is equal to this other. I will give a name to these configurations to make it easier and call them scenarios. In the first case, you started from scenario 1, moved forward in time and got to scenario 2. In the second case, you started from scenario 3, moved backwards in time and got to scenario 2. So here's what I'm getting at. Just from knowing these 2 things, can you say without 100% degree of certainty that from scenario 1 you can get to scenario 3? The answer is yes, because both of these scenarios go through scenario 2. So here's a broader question. If you have a scenario, and you also have a scenario which leads to it, and a scenario which can come after it, are those 2 connected? Can you get from the scenario before to the scenario after? Again, the answer is logically yes. It's like saying that 2 comes after 1 and 3 comes after 2, so 3 comes after 1. I know this is very obvious, but I wanted to make it clear because now I'll start doing stuff with infinite amount of pegs and the situation will quickly become unintuitive. Say that you have a single vertical line of pegs starting at 0, 0 and then going on for eternity. One thing you could do is use the second peg of the line to jump over the first one and get to 0, 1. Then you could use the fourth peg to jump over the third one and repeat this process forever. In an infinite amount of time, you would end up with this configuration. You can see it as a vertical line of pegs starting at 0, 1 and going on forever, having pegs just in points with an odd y value. In this case, this is scenario 1 and this is scenario 2. So here's scenario 3, a single peg in 0, 2. What configuration of pegs could bring you to this scenario? Well, this one for example. But then, what configuration of pegs could bring you to this new configuration? This one. Keep going for another 3 or 4 steps. Actually, keep going forever. And eventually, you get to scenario 2. Same logic as before. Scenario 1 leads to scenario 2, which then leads to scenario 3. So from scenario 1, you can get to scenario 3. That means that if you have an infinite vertical line of pegs, you can convert it into a single peg standing 2 spaces over the first peg of the line. Clearly this seems weird and unlogical, right? It makes sense, seeing the previous scenarios example I made, but it's still strange. Well then, let's check the now formalized rules. Does this move break any of the rules? No. Moves are made one at a time, and in the correct order, and in the correct way, so this move is legal. And it has been called the whoosh. Before moving on, there's just another thing to clarify, and it has to do with time. Remember the function that tells you the state of the game? Well, you had to input a time in that function so that you could see the state of your game at different instances of time. But how can you see the various states of the whoosh? This is scenario 1, 2 and 3 of the whoosh. But to get to scenario 2, you have to make an infinite number of moves. So this is the board in the first moment, then in the second, the third, but what do I have to input if I want to see the board in the moment where scenario 2 is reached? I can't input infinity. And then what about the other moves after scenario 2 is reached? What about scenario 3 and after that? To solve this problem, don't make your move at t equals 1, but rather at t equals 1/2 or 0.5. Then make your second move at 2/3, which is slightly bigger, 0.66. Make your third move at 3/4, again slightly bigger, 0.75. This is useful because these fractions keep slightly increasing but never reach infinity. Actually, they never even reach 1, they go on for eternity. And now you can say that at time t equals 1, that's where you reach scenario 2. Then after that, you can move on in similar style and reach scenario 3 at time t equals 2. And so you can easily track and find your moves. For this next part, moving backwards in time is again needed, so you need to become familiar with it. A single peg can always become 2 pegs adjacent to it. Since an infinite line of pegs can whoosh, a single peg can always de-whoosh in every direction. And that's it. Now I'll proceed. Start with a peg at 0, 3. It becomes 2 pegs, then they both get de-whooshed. Now this peg becomes 2 pegs, and they in turn both get de-whooshed, and so on forever. After this is done, you get somewhat of a staircase. Take the upper peg and de-whoosh to the left. Then keep looking at the staircase edges. skip the next one and de-whoosh the one after. Then skip the next one and de-whoosh the one after, and so on. After that, this peg can become 2 pegs, and this one can become 2 pegs. And actually, now you can keep doing this until you get a square. And this square is actually part of the starting point. Starting from here and moving backwards in time, you can get here. So that means that starting from here and moving forwards, you can get here. This move is called a mega whoosh. With it you can convert a quarter of your plane into a single peg at 0,3. Now, ready for the proof? Here's the start. Your first move is to mega whoosh the left quarter to 0,3. Now whoosh the central normal line at 0,2. Now jump from 0,2 to 0,4. Mega whoosh the right quarter at 0,3 and jump from 0,3 to 0,5. And there you go. Level 5 has been reached, and as the decreasing monovariant proved, you were only able to reach it using a single peg. Thank you for watching.